This module introduces the A320 electrical system. The electrical system provides both alternating current and direct current power to operate the aircraft systems. AC power can be generated on board, and when on the ground, AC power can be provided by an external AC power source. The aircraft is equipped with 5 methods of onboard generation of AC power: 3 generators, 1 emergency generator, and a static inverter. Let's look at them a little more closely. There are 3 AC generators installed. These generators are the normal source of AC power. There is 1 on each engine and 1 on the APU. The generators are rated at 90 kVA. Normally during flight, AC power is supplied by the engine-driven generators. When the aircraft is parked, AC power may be provided by the APU generator or an external ground source. The aircraft is also equipped with a ram air turbine, RAT, hydraulically powered emergency AC generator that automatically operates in flight if AC-1 and AC-2 buses are not powered. The emergency generator is not considered one of the normal operating generators. In the event that no generators are available, a static inverter is installed to provide yet another source of AC power. The inverter converts DC power to AC power and is powered by battery 1. Please review the 5 methods available for the aircraft to provide onboard AC power. Now we'll describe the sources of DC power. Aircraft DC power is normally provided by converting AC power through the operation of the onboard transformer rectifiers, TRs. There are 2 normal TRs and 1 for essential power. The normal TRs can each supply the DC system with up to 200 amperes of DC current. The essential TR can power the essential DC circuit from the emergency generator if all normal generators have failed, or TR1 or TR2 has failed. Each TR controls its contactor by internal logic. An alternate source of DC power is the 2 aircraft batteries, designated Battery 1 and Battery 2. Each battery has a normal capacity of 23 ampere hours and is permanently connected to the respective hot bus. Each battery has an associated battery charge limiter, BCL, that monitors the battery charge and controls the battery contactor. Okay, let's look at the electrical system diagram. The electrical system consists of left and right sides. The 2 sides are normally isolated by 2 open bus tie contactors. In flight, each side is normally powered by the respective engine-driven generator. To improve dispatch reliability, and with some operational restrictions, the APU generator may substitute for an engine-driven generator. In this case, 1 bus tie contactor will be closed for the side that the APU generator is powering. While only 1 generator is operating, it can power both sides of the electrical system through the bus tie system. You should know that although 1 generator can power both sides through the bus tie, there is never a time that generators are paralleled on the same buses. The 1 operating generator could be one of the engine generators or the APU generator. Okay, you've learned that there are 2 engine-driven generators and 1 APU-driven generator. All 3 generators are identical and provide the same capacity. The generators provide 115/200 volt 3-phase, 400 Hz AC power. Any one generator is capable of supplying all essential AC power to the aircraft. Each engine generator has a generator control unit, GCU. The GCU controls the output of each generator and provides protection to the electrical network. Specifically, the GCU controls the voltage and, through the integrated drive generator, the frequency of the generator power output. While the generator output is normal and there are no system faults, the GCU will command the generator line contactor, GLC, to close and allow the system to be powered. If the generator output is abnormal or if there is a fault in the system, the GCU will command the GLC to open. The Ground and Auxiliary Power Control Unit, GAPCU, provides similar functions for the APU generator and external power, that the GCUs provide for the engine generators. For the APU, in order to maintain a constant voltage and frequency, the generator drive speed must remain constant. Since the APU generator is directly driven by the APU, the drive speed of the APU generator is maintained by control of the operating speed of the APU by the GAPCU through the ECB. For external power, if the ground power source is normal, the GAPCU will allow the external power to be selected on and power all buses. The engine-driven generators are each driven by an integrated drive generator, IDG. The IDG provides a constant drive speed to the generators, regardless of the engine operating RPM. If the IDG malfunctions, the flight crew can disconnect it from the engine drive, thereby shutting down the respective generator. Earlier, you were introduced to the emergency generator. The emergency generator is driven by hydraulic pressure from the blue hydraulic system. The emergency generator can also receive this hydraulic pressure through the operation of the ram air turbine, RAT, that automatically deploys during a total loss of normal AC power. The emergency generator is rated at 5 kVA, 115/200 volt, 3-phase, 400 Hz AC power. It can provide power to the essential AC bus and through the essential TR to the essential DC bus. If no other source of electrical power is available, Aircraft Battery 1 can provide a limited source of AC power through a static inverter. The static inverter is rated at 1 kVA and provides 115 volts, single phase, 400 Hz AC power. Now we have an overview of the system components. Let's look at the electrical system diagram. The diagram flows generally from the bottom to the top. AC power is supplied by an engine generator, the APU generator, or external power. On this frame we show the engine generators providing the power. As shown here, the bus tie contactors are normally open and the engine generators are online to power their respective side. Power flows from a generator through a generator line contactor, GLC, to the respective AC bus. The AC power flows from the AC buses up to the associated transformer rectifier, where the AC power is converted to DC power. Notice the AC essential bus. It is normally powered by AC bus 1, but can also be powered by AC bus 2 or the emergency generator, or even the AC static inverter if necessary. The AC essential bus normally powers the AC essential shed, and as its name implies, the AC essential shed can automatically shed to reduce the electrical load on the AC essential bus. Okay, let's go back to the DC power. After the power is converted by a TR, the DC power normally flows to the respective DC bus and then on to the DC battery bus. From the DC battery bus, the DC power normally flows down to the DC essential bus and then to the DC essential shed. The powered DC battery bus also provides power down through the battery contactors to the hot bus 1 and hot bus 2, and then to the respective batteries for charging. Take a moment to look at this diagram and imagine how power would flow if it was provided by the APU generator or external power. When APU or external power is online, the bus tie contactors will close to allow the APU or external power to deliver to both sides. Here we show a loss of all normal power sources. Look at the emergency generator. It can power the AC essential and DC essential buses when no other generator is available. It takes 8 seconds for the RAT to deploy and the emergency generator to produce power. During the 8 seconds, batteries and the static inverter keep the AC essential and DC essential buses powered. As another backup power source, the static inverter can power the AC essential bus, while at the same time, battery 2 can power the DC essential bus. The static inverter operates if the aircraft has no other power except the batteries. All right, we have an overview of the system diagram. Let's locate the controls and indicators in the flight deck. The controls and indicators in the flight deck consist of the electrical panel, the emergency electrical panel, and the ECAM electrical page. Take a look at the panels and displays as they are shown here with a normal in-flight configuration. The ECAM electrical page displays the system similar to the diagram we have used. Let's briefly look at how you will use this system in normal everyday operations. When you arrive at the aircraft, you'll notice that external power is plugged into the aircraft, and you'll want to turn on the external power. But first, you'll perform a visual check of the battery voltage before each battery switch is selected to auto. Then, after each battery switch is selected to auto, you'll verify the external power is available, and then you'll select it on. External power will then be applied to both left and right electrical systems. Sometime before pushback, you'll start the APU. The APU generator does not automatically disconnect the external power, so if you want the APU power applied to the aircraft, you'll have to turn off the external power. When the external power is no longer in use, ground personnel can disconnect it from the aircraft. The engine generator switches are usually in the on position. Upon engine start, the engine generators will automatically power their respective side of the electrical system, and the previous power source will be disconnected from that side. After the engines are both started and the APU power is no longer in use, you will shut down the APU. The electrical system will be monitored throughout the flight for normal operation. No other duties are required. After landing, you will normally start the APU, or, if the APU is inoperative, wait for external power to be plugged in at the gate. If the APU is running when the engines are shut down, the APU generator will automatically power the electrical system. If the APU is not used upon arrival at the gate, and the external power is plugged in, you will simply select the external power switch to on. Since the engine-driven generators have operational priority over external power, they will continue to power the electrical system until both engines are shut down. Note, you won't want to shut down the engines until external power is available and selected on.
The aircraft buses are normally powered using the following priority. Engine generators have priority over external power, which has priority over the APU. A single engine generator will power all electrical buses. However, with two generators online, each generator powers its respective side.
The order of the bus power source priorities is 1. Engine generator to on-side bus. 2. External power to unpowered bus or buses. 3. APU to unpowered bus or buses. 4. Opposite side engine generator to unpowered bus. Let's answer some questions for the information presented in this module.